Hey math people, integration by parts is not easy. It's substantially more involved of a process than U substitution. U substitution, pretty much just, hey, find the thing on the inside, that's your U, take the derivative, plop it in, cancel away, it's integratable. Yeah, okay, not with biparts. With biparts, you can run into a lot of issues. You can run into a situation where you might have to do biparts many times over. You can run into a situation where the case of the unknown integral is great. Neither of those is the point of this video. You can also run into situations where you get maybe a pretty tricky integral for the second part of the expression, or maybe you have to do a U sub within a biparts, or blah blah blah. There's many different tricks that can come into play. Let's just do two of them. So this is not going to be case of the unknown. This is not going to be tabular, which means multiple integrals in a row. These will be different tricks you may encounter. So let's look at the first one here. X times cosecant square of 5x dx. Looking at the formula, the general advice I advise is that your U choice should just be the simple one. And your dv should be something you can integrate. And usually you're good to go if that's how you select it. So which of the two is simpler of my two factors, the x or the cosecant square 5x? Well, the x is the easy choice, so this is going to be my u, and all the rest will be my dv. So let's see what happens here. I need to now figure out my du and my v from this, so we have to do some derivatives and integrals now. So u is equal to x, making du dx, so taking the derivative of both sides with respect to x. Derivative of x is just 1. So therefore du is equal to dx. And then looking on the other expression here, I have dv is equal to cosecant square 5x dx. Okay, so let's move this dx over. So dv over dx is equal to cosecant square 5x. Now I have to integrate both sides. So integral of left here is easy, that's just v. So I'm integrating with respect to x here. What is the integral of cosecant square 5x? We have to be careful here. What is that integral? I know that, so I'll do this off to the side. I know that ddx of cotangent x is equal to negative cosecant square x, right? So I want to use that to my advantage. Just two little minor issues is that this isn't negative, and I wanted it to be, so that's going to be negative. And the 5 is going to be an issue, but we'll talk about that in a second. Let's write down our cotangent of 5x here. If I were to have taken the derivative of this, oh shoot, I would not get this because of chain rule. The derivative of negative cotangent of 5x is actually 5 times cosecant square of 5x. Because I have this 5x on the inside and I have to do chain rule. So in order to get rid of that 5 up front, I'm going to make this a negative fifth. So if I take the derivative of this expression, derivative of cotangent 5x is negative cosecant square of 5x. Okay, so the negatives go away. And then, well, chain rule, multiply by 5. The fifth and the 5 will cancel out. So now it's a match. This is my v. Alright, so that is my bipart choice. Let's now say that this integral is equal to uv, so this times that. And yikes, that's a pretty complicated expression, but who cares because it's outside my integral. So that's part of your answer. That's my u, that's my v, that's the product, minus the integral v du. Okay, I have this negative 1/5 as a coefficient, so I'm going to pluck it outside the integral and make it, so a negative 1/5 is going to go out here, a negative is a positive, and now I don't have to worry about that fifth anymore. So I have this cotangent of 5x. And then now du, and hey, look at this. This is why I like simple choices for u. My du is just dx. But unfortunately, I'm not done. If you happen to not know the integral of cotangent of 5x, or just generally the integral or antiderivative of cotangent x, you got to do this the long way. And I'm going to do this the long way. It's nothing too crazy. It just means we have more work to do. Right, so negative x over 5 cotangent 5x plus 1/5 the integral. But man, how do I approach this in an intelligent manner? Okay, how can I rewrite cotangent using the quotient identity? What goes over what? Is it sine over cosine or cosine over sine? No, I'm asking which one goes up top. It's cosine, right? Because tangent is sine over cosine, yeah. So it's going to go cosine of 5x over sine of 5x dx. Why would I do that? Why would that be helpful? I know the derivative of sine is cosine, and how might that help us if I perform a u sub? But the problem is, and this is just a me being picky kind of thing, I already used a u, so sometimes what teachers will do, if you have, say, a u sub inside of a u sub, that's like the worst case scenario you can run into, is you use the variable w. So I'm going to do that just for the sake of, I don't know, being collective here in my thought process. I want to use a w sub. And what I could technically do is, this expression is not easy. I could say w is equal to 5x, and then I could do another sub, so this would be a u sub and a u sub, but I don't want to do that. I can just big brain this. That's what I say. Anytime you have a function and a function where the inner function is linear, you can big brain it. That's what I say. And you can just kind of think about what could happen. And actually, we already did that. We big brained it right here because we could have used a u sub for this 5x, but that's just being a little extra. I think it's better to just kind of piece it together in a different way than that. So anyway, I'm going to do a w sub here. I'm going to say w is equal to, well, I know the derivative of sine is cosine, so that's going to help me with u sub. So I'm going to say w is equal to sine of 5x. So therefore, dw dx is equal to, this is going to be cosine of 5x, however, chain rule, so it'll be 5. And then I want to solve for dx here. So dx, I'm going to bring the dx over here and then divide by this expression, is dw over 5 cosine 5x. Okay, let's see if this helps us. Sure hope it does. A lot of rewriting. Negative x over 5 times cotangent of 5x plus 1/5. Let's get to it. Let's do this w sub now. W is equal to sine of 5x, so this is going to be all over w. That's nice. My cosine of 5x, oh no, it's still sitting there. Let's see and hope something happens. And here, I'll just kind of be fancy with my color coding, I guess. This was w. Okay. And then my dx is equal to dw over 5 cosine 5x, which is really nice. I like this because this cosine 5x right here cancels with this cosine 5x here. And actually this 5th is just a constant, so I can bring it on outside. 5 times 5 is 25. So what am I left with? I'm left with just the integral of 1, because these cancel, over w dw. So I'll just kind of write that over here. What is going on? Integral of 1 over w dw. That's what that cleans up to. And I actually like this integral. It's just the natural log of the absolute value of w plus c. So I'm going to apply that here. Oh man, running out of room. Negative x over 5 times cotangent of 5x plus 1 over 25 of the natural log. And it's safe to put absolute value of w, but I know that w is equal to sine of 5x. And then at the very end, don't forget your plus c. That'd be a bad way to go out if you got everything right but the plus c at the end, bringing you to a final answer for this one. So, man, that's crazy. What made this by parts a little tricky? Technically, there were multiple opportunities for u subs. That's the first part. This one you really couldn't avoid if you didn't know the integral of cotangent. So, yeah, these can get really fun. By part problems, I love by parts. I think as a calculus teacher, I'm going to be looking forward to January every year, because that's when I plan to hit by parts moving forward. So, yeah, it'll shed some light to my Januaries. All right, let's do another one that's a little bit harder, actually. Okay, looking at the next one. Integral of x cubed times e to the 3x squared dx. It is super tempting to try a u sub here, and I encourage you to. I encourage you to do it, and I encourage you to fail in doing it, because it's interesting to see why it fails. It's ultra tempting to say u is equal to x cubed. Okay, so that would make du dx equal to 3x squared, because it's up here. That seems like a bright idea. No, because this is up in a power, and it will not cancel out the way you think it will if you were tempted to doing a u substitution. So not going to work. You know what else is not going to work? Choosing a u and dv in the representation it's currently in. In my opinion, it is super tempting to say, oh hey, you're my u and you're my dv. That also won't work. In fact, the opposite, I'm not sure, I didn't try the opposite, but I don't like that way either. We have to be more creative for this setup, is what I'm advertising here. The current setup for it is not something that's going to help us out. We need to play around with it in a more creative way. Let me at least show you why the first more obvious by part setup doesn't work. If I made this my u and I made this my dv, I'll at least show you why that doesn't work. So if I attempted to do that, that would mean that I would think that this is an easy integral, but that's not the case. If I attempted to take the integral of e to the 3x squared dx, just sit and tilt your head and attempt to do this one for like 20 seconds. Good luck, because it's not that easy unless you're like randomly I don't know, someone who's way further than Calc 2 watching this video, in which case I don't know why you're watching this video. This is not something we know how to integrate through the ways that we know how to integrate here in Calc 2. So with that said, shoot, I need to be more creative. If there was a particular variable off to the side, this would be an easy integral. I could do a u sub, because the integral, or the derivative of 3x squared is just 6x. So if there was an x here, man, this problem would be easy. If there's only some way somehow I can get an x here. If maybe one of my factors could lend an x over to e to the 3x squared, that would be great. Who has an extra x just laying around? Oh, look at that, x cubed. You have an extra x just laying around. Why can't I, and I can, so there's no answer to this, why can't I just write it like this? Why can't I say this is equal to the integral of x squared? Let's lend him an x. X times e to the x squared dx. You absolutely can do this, and this we shall do. And this will also help us see that our choices of u and dv going to be a little helpful here. All right, so let's convince you why these are good choices. U is equal to x squared, which means du dx is equal to 2x, bringing you a du of 2x dx. My dv is x e to the 3x squared dx. So what is my v going to be if my dv dx is x times e to the 3x squared? I have to integrate this expression, and that's an expression I know how to integrate. I will do so in a different color. We'll do it in red. So this is not a part of the problem. It is a part of the problem, but it's not a part of this equality chain. So yeah, let's integrate this. Let's take the integral of x times e to the 3x squared dx. I suggested a u sub, so a u sub we shall do. Yeah, we'll use this color. So I think a u choice of 3x squared is going to be really helpful here, such that du dx would be 6x, so therefore dx is going to equal du over 6x. Oh, don't throw that one there just yet. So I'm going to say this is equal to the integral of x, this didn't change, he's still chilling there. This e, that didn't change, he's still chilling there. Now it was once to the 3x squared power, it's now to the u power. So this is going to be to the u. And I know that dx is equal to du over 6x here, so I'm going to plug that in as well. This is a 6. Alright, now I'm done with this. So what happens? These x's cancel. That's what we wanted. That's the reason why this didn't work by a u sub, and this does. So those x's cancel. This sixth is brought up front. So it's the 6, and this is equal to 1/6 times the integral of eu du. I know this antiderivative is just e to the u. So 1/6 e to the u plus c. And then very finally here, I knew that u was equal to 3x squared. So this will be 1/6 times e to the 3x squared. Wow, that was a lot of work just to figure out a small part of a large problem here. And if you're a color coding fan like me, you kind of run out of ways to carry markers. So v is equal to 1/6 times e to the 3x squared. Okay. All right, let's do some voodoo stuff. uv, so what is this going to be equal to? Done with green. Should almost throw the markers on the ground that I'm done with. Done with green, I think. This is going to be equal to uv. So this will be x squared over 6, and then times v. I started the v already, as you can see, times e to the 3x squared minus the integral of v du. And man, let's hope that the integral of v du is manageable. So what's my v? It's this thing right here. And if you don't mind, I'm going to pull out the coefficients. So it's going to be a 6th e to the 3x squared times du, which is 2x dx. 6 times 2 is a third, so I'm going to have a third chilling up front. Alright, so then what's left on the inside here? It's going to be, so this one away, this one away. I still need this x from the du, and I still need the rest of my v. I already took care of the 6. This is going to be e to the 3x squared. And hey, I already found the integral of that. That's the beauty behind this, is that it's right here. Oh no, I forgot the plus c earlier. But it doesn't matter. That wasn't a part of my problem. Anyway, this is the integral right here of x times e to the 3x squared. It was already part of the problem, which is really nice. So I'm actually going to just straight up jump to that and pretty this up through some algebra. I get x squared over 6 times e to the 3x squared minus a third times this expression, because these are identical, they're the same. So it's going to be times 1/6 times e to the 3x squared. And technically that ends the problem, so don't forget your plus c like I did over here. Let's just do some, we already went, this is already extra, by the way, this is already extra, so let's just go overkill with this, and let's just make this expression as pretty as possible. This is an 18th e to the 3x squared, so let's make this an 18th as well by multiplying by 3. So it's going to be 3x squared times e to the 3x squared over 18 minus e to the 3x squared over 18 plus c. So I can now combine, and I end up getting 3x squared e to the 3x squared minus e to the 3x squared over 18 plus c. And let's just finish this. This is a common factor amongst them. Let's factor this out. So a final, nice pretty answer of e to the 3x squared times 3x squared minus 1, because I factored it out there, all over 18 plus c. I definitely went in the glare zone somewhere, so here I'll just use my body's shadow so you can pause it at some time to read it. Yeah, oh, there's the glare zone, okay. Yeah, that's the problem. So I'm going to ask you to math on. I will do the same. If you want to see some more crazy by-part problems, I suggest you look up case of the unknown integral and tabular method or DI method. Those are other ways to have a tricky by-part. And then the other tricky by-part setup, doing another color that you can do at your own leisure. And where the heck am I going to put this? Integral of arc sine x dx. This guy right here, you wouldn't think it is, but it is. It's a by-part problem, and you need to be creative in your choice for u and dv. So yeah, math on. I'll do the same. I already said bye, so this is the second bye. See you in the next video.